Welcome back, everybody. We're in the middle of proving our first structure theorem in inner product spaces, the one which is currently displayed on the slide. So in an arbitrary inner product space, you have these three cute identities. Number one, the parallelogram identity, which we proved at the end of the last video. We have the Pythagorean theorem, which we will prove now. And once the Pythagorean theorem has been established, it has an important corollary to it, which is called Bessel's inequality. And it is really a corollary because if you have the equality up there, the only thing that you do is you drop this non-negative term and immediately get the inequality as stated. Okay, so now let us prove Pythagorean theorem. So at Pythagorean theorem, So the Pythagorean theorem involves the following quantity that you might remember from linear algebra class, especially if you think about orthogonal projections and the Gram-Schmidt algorithm, which will reappear, by the way, here in this class as well. So let's just for now introduce this abbreviation. So yxj inner product, that gives you a scalar, and then you hit that scalar with the vector xj. The xj's, they form an orthonormal set, and then you sum them up, and you get vector y. Okay. Then here's a short computation. So y hat. Okay, and once you have some exercise with inner products, this doesn't require much work anymore, but since this is still very early on here in our class, so I will do the details. Now what you can do is you use the properties of the inner product, you get the sum out, but the scalar, this one here, once you move it out, it comes with a complex conjugate bar on top because the inner product is conjugate linear in the second vector. So what you get here is j from 1 to n, then yxj, complex conjugate bar, that's what I pull out. And then what is left? Maybe allow me to move this to the bottom here, like so. And erase this, yeah, so that we have more space. So this is the scalar factor that I pull out and decorate with the complex conjugate bar, and then what is left inside is y xj. All right, but this is again complex number times its complex conjugate. This is the complex modulus squared of the same number, so y xj squared. Okay, this was easy. So we have this is equal to this. We will use it in a few moments. Now the next one that I compute, so far we haven't used the fact that this is an orthonormal system at all. So but now we will. So inner product y hat with itself. Okay. So now you have that sum in both entries, yxj xj, and then different summation index k in the second one, xk, and inner product. And then again you play the same game. You exploit the properties of the inner product. Those sums go out, this one and this one. The scalars also go out. The one in the first vector goes out as is, and the one in the second vector goes out with a complex conjugate bar on top. Okay, what you get a double sum, jk from 1 to n, yxj, then yxk bar, and then what remains is the inner product xj with xk. And now at this point you use that you're working with an orthonormal system, because by definition this guy is almost always 0, precisely when j is different from k, and otherwise it is equal to 1 when j is equal to k. This was built in the definition of an orthonormal system of vectors. You can check your notes. Okay, yeah, but now with this requirement, out of the double sum, only the terms, well, so to say, on the diagonals survive when j is equal to k, and if j is equal to k, well, then again, this is the complex modulus squared of inner product yxj, which is the same result as in the last computation. Okay, therefore, we have y minus y hat squared. This was one of the quantities in the Pythagorean theorem. Now remember earlier in the proof of the parallelogram identity, we had this identity. This is sort of know by heart thing. It's super easy. Plus minus 2 real part xy. So let's do this here. Let's use this equality here. So I have y squared plus y hat squared minus 2 real part y hat. And now all these two quantities here we computed, because this is inner product y hat with itself. So it is y squared plus, the result is still up here, j1 yxj squared. This is precisely this here. Okay. And the other one was the one on the previous page. It was real because it was a sum of complex moduli squared. So I can drop the real part and I just have yxj squared. And now you see here quantity appears once and here twice, and it's subtracted, and this precisely gives you the result in the sense that it is the Pythagorean identity as claimed in the theorem. Okay, this is it. Bessel's inequality again comes out by dropping just one term. Good. Now, these easy things have very important consequences. That's why we do it. The first one, corollary, gets its own corollary, is Cauchy-Schwarz. Inequality. So let V be an inner product space with, again, this quantity. Still, we don't know yet if that is actually a norm. So for now, it's just an abbreviation. Then this abbreviation satisfies for any xy in V the following inequality. Well, Cauchy-Schwarz. Okay, that's what we have. How to prove it? Okay, there's many proofs of Cauchy-Schwarz inequality, of course. Usually one doesn't use Bessel inequality to prove it, but here we do. That's why I did Bessel first. So if x is equal to 0, the 0 vector, well then this here will be equal to 0, and the inner product, because it's linear in the first vector, so if you stick in there the 0 vector and hit it with anything else, it would also be 0, right? And certainly 0 is at most equal to 0. So that then inequality is clearly true, all right? Then star is true. So assume x is different from 0 and set x1 as x divided by norm of x. Then this set here, consisting of one vector itself, is a finite orthonormal set. Well, it is orthonormal. Orthogonality, nothing remains to be checked, because there's just one vector in there. So you can't have inner product of this vector with some other vector equal to 0 when the indices are different, because there's only one vector in there. But it has length 1, so Bessel inequality applies. Then is a finite orthonormal set. So by Bessel's inequality, so Bessel's inequality was on the left. There was a sum from 1 up to, well, as many vectors as are contained in that orthonormal system, but here it's just one, right? So I have y x, well, xj first, yxj squared, and since there's only one vector in here, this is just yx1 squared, and Bessel's inequality says that this is less than or equal to y squared. Yeah, but this is precisely Cauchy-Schwarz, because this guy here is x over norm x, so you bring the norm to the other side, you take a square root of the entire inequality, and you get precisely the star, aka the Cauchy-Schwarz inequality. Okay, so that's this very, very quick proof, provided you have Bessel's inequality. Good. Now finally, corollary of Cauchy-Schwarz. Every inner product space is a normed linear space. Every inner product space V is a NLS with norm, well, the one that we have been carrying around now for quite a time, xx and square root, non-negative. Okay, proof. So since V is a vector space, we only need to check that this quantity here defines a norm. Alright, normed linear space is a vector space with a distinguished function, a norm on it, and the norm satisfies 3 properties. So we have to now check whether these properties are satisfied with this object. Okay, well, there's not really much to be done anymore. So the norm property, the definiteness, is that this is 0 if and only if the vector is equal to 0. But look here, if this is 0, then this means that this guy is equal to 0, and this is one of the axioms of the inner product, that this will only happen when x is equal to 0. Okay, so this is good. The fact that you can pull out scalars, aka that the norm is homogeneous, this is also good. You have lambda x. Now you pull it out from the first factor as is, from the second factor it gets a bar on top, and then you have xx, like so. But this is precisely complex modulus squared, so indeed this is lambda x. Okay, so also there everything works fine. So the only thing, as usual, is the triangle inequality. Okay. We only need to discuss the triangle inequality. Okay, so again, standard computation, x plus y. Remember that formula. This is x squared plus y squared plus twice the real part, xy. Okay. But now, what can we do? So that real part is a real number, so I can bound it by, well, in easy fashion. So I will write down what I want to say, and then I'll explain it. X squared plus norm y squared plus complex modulus of xy and a factor 2 out front, because it was twice the real part. And why is this? Well, simply because whenever you have a complex number, this is the real part of the number squared plus the imaginary part of the number squared. So it is, of course, at least, because this is non-negative, at least as big as the absolute value of the real part. And that's what you use, because in the previous slide you got twice the real part, and of course the absolute value is at most as big as the number itself. So you use this in red. Stick it in, then you have this, and now you use Cauchy-Schwarz. That's why we proved it first. So Cauchy-Schwarz tells us that this is norm squared of x plus norm squared of y plus twice x y, and this is a perfect square. This is the x plus y, everything squared. And then you take the square root of the whole thing and you get the triangle inequality. Okay, so that's it. So the upshot of this is whenever you are in a product space, then you are in a normed linear space, because every inner product space is a normed linear space. We just proved it, and we know how to define the norm now. This, by the way, is gets a name sometimes, this norm here. So some people call it the induced norm, in the sense that the inner product that you start with on the inner product space, it induces this norm. Okay. Now you can ask a very meaningful question, namely, knowing now that every inner product space is a normed linear space, you can ask yourself if in every normed linear space the norm is induced by an inner product. Okay, and this is not always the case. Sometimes, at least when I teach my linear algebra course, I discuss this. You can, for instance, think about the one norm on say Rn or Cn. If you look at this object, so x is a n-dimensional vector, and now you can ask yourself whether this norm is induced by an inner product. So the question whether there exists some inner product such that this is true, and the answer is no. Okay, this is a theorem that we will now write out and you will prove in the exercises. It's surprisingly simple. It's the Jordan von Neumann theorem. Okay, let's write it out. So let X be a normed linear space over f equals c, then this norm comes or is induced is induced from / by an inner product if and only if that norm obeys the parallelogram identity. Okay, we discussed the parallelogram identity earlier. How did we prove it? Well, we exploited the properties of the inner product. In general, in an arbitrary normed linear space, it is not true that the norm satisfies the parallelogram identity in general. Okay, this is true certainly in inner product spaces, but actually the parallelogram identity, it helps you to sort of sort out those norms that come from an inner product. Okay, this is a very, very curious theorem, and it explains why, by the way, this up here does not come from an inner product, because you can easily construct a counterexample to the parallelogram identity. Again, as I said, we will address this in the exercises, but this is really a theorem to remember. We won't have much use for it in the rest of the class, but if someone ever asks you, hey, is this norm induced by an inner product, keep this theorem please in mind. Okay, good. Now, having talked now about inner product spaces, now let's connect this to analysis, because so far the material that I've discussed you can just discuss in linear algebra, and actually in my class when I teach it I do that. So far there's no analysis whatsoever. Everything is finite, everything is just algebraic. But now we become analytical. So what is a Hilbert space? A Hilbert space is an inner product space which is complete in the induced norm. Okay. So what I want to say by this, I mean, remember, so when you have an inner product space, you have this pair, and you can use this guy to define the norm. Okay. And once you're in a normed linear space, you're in a metric space, so you know what I mean by completeness. That means Cauchy sequences are convergent. Okay. There are a few other terminologies floating around in the literature, but they won't play much of a role in our class. I've summarized them in the lecture notes I just see here. But instead, let's move on. So let's do now examples of Hilbert spaces. Now this is harder to prove whether a given space is a Hilbert space, because what you have to show is that the space is now complete. First you have to figure out whether there's an inner product on that guy, or whether the thing that I write down defines an inner product, and then you have to decide whether this actually is a complete space. Okay, so that requires more work. So the first example though is easy, because we know something about finite dimensional spaces. So on Cn, this guy, just the dot product, oops, Jn xj yj defines an inner product, and since Cn is finite dimensional, this one, Cn, is a Hilbert space. And why is this? Well, because of the equivalent norm theorem. The equivalent norm theorem had three parts to it. One about bounded closed sets being compact, one about being norms being equivalent, and one about being the space is complete, right? All finite dimensional spaces are complete. So this one here in particular, because we have an inner product on it, is a Hilbert space. Okay, that was easy. Now, more challenging. Let's go to our functions. So on C01, this guy, talked about it in the last video, defines an inner product, but this is not a Hilbert space. Is not complete, hence not a Hilbert space. Okay, so now we have to prove this. There is some, of course, intuition behind it that I will try to explain now in the example. So what I have to do is I have to construct a sequence of continuous functions, which is Cauchy sequence, but which has no limit in this space here, as written here in the example. Okay, so consider for n in Z at least 2, the piecewise continuous functions. So I will write down the formula and then I will draw a picture, and then probably the idea is clear what I'm doing here. So we go from 0 up to 1/2 minus 1/n. That's why n should be at least 2, otherwise you're in the negative numbers there. And then above 1/2 it is constant 1. And now what you do is, so you will have a piece which is 0, you have a piece which is 1, and now you connect them with a straight line, so that the whole thing is continuous. Okay, and you can easily think out what the formula is. It is n times x minus a half plus 1 over n. Okay, so 1/2 minus 1 over n, x bigger than that, strictly bigger than that, and 1 over 2. So indeed, what I was just saying, the picture is, say, like this. So here's 1, here's 0, and then, well, here's a half, and we kind of creep up to that. And out here it's 0, somewhere here it's 1, so this here is a half minus 1 over n, and now you connect with a straight line. Okay, so this is certainly the graph of a continuous function. Now, but what happens as, well, n goes to infinity? Well, this will move to the left here. That will shrink to 0. So that thing, well, at least geometrically, you would believe it will converge, hopefully, as n goes to infinity to a, well, a non-continuous function which jumps. Okay, and that's precisely what happens. And but this we have to prove. We now have to prove in the next video that indeed this is a Cauchy sequence in, well, this norm induced by that inner product up there, but that it doesn't converge to anything continuous. And then in turn we are able to conclude that that space is not a Hilbert space. Okay, this I will do in the next video. Besides this example, we will then look at sequence space and there actually derive a positive answer about the sequence space small L2 with the inner product that we discussed earlier is a Hilbert space. Yeah, that's right. Once done, then we will develop more theory. Okay, I will see you in the next video.